Hello and welcome. Today we're going to talk about root cause analysis. So, what does it mean? Like today we're looking into, I face a typical problem and I want to find out what is the source of this problem or what is the cause of the problem. And a root cause analysis is a typical task for descriptive analytics. We want to know why a certain scenario has happened, either once in a lifetime or over and over again. Typically, example could be, I want to know why my product quality is currently bad, or I want to know why a certain scenario just happened. Or a typical example, which I as well did already multiple times with different clients, is about, I want to understand why is a certain machine performing differently or worse than other machines. Like for instance, we are here now in our virtual machining room, overviewing the shop floor, and we can see our different milling machines. And we can see like most of them are running well, OE all fine, but for one machine, something is off. And we want to understand now deeper, why is a certain CNC milling machine failing all the time? And the trick with the root cause analysis is, if we just check historical data, by just plotting all over everything next to each other, we have typically no chance to figure out why it's failing, what went bad, or what's going on. And even if you check the live data to compare it maybe to it, as well, no, just because we see some live data doesn't help us to see like, that's why it's going bad. Sometimes you're lucky, you have one condition which is just shooting over, like a vibration, a temperature signal, then it's clear. But a lot of the time it's somewhere hidden between the multiple dimensions of the different parameters. So to figure out what's going on, we need to perform a root cause analysis. And that's what we are going to do today. We are now taking that example of our CNC machines, and we want to figure out why is one of those machines failing actually. And therefore, we are now, first of all, need to grab the data and combine it, because we got here some data from our process historian where all the real-time data was stored, or maybe for instance our influx database. And on the other hand, we are having here some MES data, which can come from a MES system, SQL database, or whatever. And we perform some manipulation like replacing missing values and some tasks before to then combine those two data streams so we can analyze them together. Because as more of different data sources we can put together into context, as easier it gets to us to understand why is a machine failing, not failing, because as more data we're getting, as more context we're getting around those events. And as well, we're having here in green marked what you can see, a column which is already telling us false or true, which means that when our machine has failed or not failed. And for a root cause analysis, the first step typically what we do is we check like, okay, how many of those events we are having? We're having 339 events of when the machine is going to fail and 9,661 when it's not going to fail. And by, for instance, just checking now all the distributions, min, max, so on, still super hard to understand root causes. What already might help is if we check the data into more detail. So maybe we can now colorize the different distributions to check what's the distribution of the air temperature, for instance, when it's like true or when it's false. But still, the distributions there are looking quite similar. Another thing is maybe we want to check this for the rotational speed still. Just by visually looking into it, hard to find, but you can see like there's some small differences. Or maybe let's check out the tool where how long the tool is running. There, for instance, we already can see like, okay, when the tool is running for a longer time, there are more true events of the failure, while false events. So already here, maybe we can get some hints, but clearly statistical proven that is the cause. Still not clear. It's just like guessing in the room, maybe getting some first feelings. Or maybe I have another idea. Maybe I use a scatter plot and try the same thing. Maybe I can find some information over the time axis, which would give me some more value about the events. But even here, even when I know when the time has come, like we see, like we have an area where there have been more failures and less failures, but it's always just like guessing in the room. So we need to do something more profound to perform our root cause analysis. And what we are doing here is now we are doing an interactive decision tree. So we first of all save now into the data set and define our decision tree. And now we select that one. And now we want to build a root cause analysis decision tree on our machine failure. And what does that mean? You will see in a minute. But before that, we first get a selection of what we should include in our data and what we should not include in our root cause analysis, because some data just doesn't make sense, like time series dependency is not the case, ID, like the product, there's some things like an ID won't give us any information. So those are already automatically deselected, but we could in series select those, but doesn't make sense. We trust the system. The next step, here are some further parameters, but we leave them as they are. And now we have the option to either build this root cause analysis tree manually, or we automatically grow it. But for now, we do this manually. So now we're having in our box all our machine failure data. Say 9,000, 6,000, 61 false, 339 true. And marked with green and yellow the false and the true ones. And now we can start splitting the data set over based on different attributes. For instance, I want to split it by the torque. And you can already see, like, now you have ranges of the torque where the likelihood is higher that the machine won't fail, and you have areas of the torque, when our torque frequency is super high, above 53,000, we see like the likelihood that a machine is going to fail is already at 18%, while here it still sticks around with 3.8%, where as well we have areas where basically failure events are not really happening. And we could now manually do the same for the rotational speed, for instance. Or as well, maybe we want to see the air temperature. And we see like, okay, not a clear visible difference. And we could now build manually our tree. And so, but at the same time, we see already percentages of the entropy explained. So in this case, the torque can explain 80% of the occurrences. So it has the highest decision power, basically. And therefore, we're going back to the torque. And now, for instance, we're having here a class where already we know like 20% of the failures roughly we can identify here. We could now create another split, maybe on the toolware. And it always, by the way, when you try find split, it will take the best split possible. It will check, okay, what would be the best possible split to split this data set further apart to understand the root cause area. And for instance, in this case, we know already from the machine failure, from the 339, we already can see like that 185 of those events occur between 52,000 and 76,000. And we can increase now even here the sample or the likelihood to 50% when the torque is high and as well the tool wear is above 174. Then we see like we even here further, and we could now check if there would be another split possibility to analyze this further. And if we zoom out, you see as well like of how much of the data set we are talking here. Here we're just talking of 1.8.6 left from the data set. And here we can create another leaf node, so to say, another root cause area where we can clearly see, okay, when the temperature is high, the tool wear is high, and the torque is high, it's quite likely that my milling machine is going to fail. Same goes when the torque is high or the tool wear is high. And with that, we can understand areas where it's more likely or less likely that a machine is going to fail. But now we did this fully manually, so we did basically human learning with a little bit support of statistics, which is not always recommended. So instead of doing this manually, we have the option to do this automatically. Therefore, we would now select our maximum depth, in this case, for instance, 4. And we would now split this automatically. So all algorithms would be calculated and build the best decision tree possible to identify the root causes. And with that, we now see areas, like when we zoom out, you see like in orange where you have like higher likelihoods of the machine failures, and as well areas with basically no likelihood. Like you see, like we're having areas around 0%, 0%, 0.96%, where we're having samples around those areas where we know like if we're staying in this production conditions, no failure will going to happen. No bad things are going to happen. We see, for instance, as well low tool temperature, but combined with high tool wear temperature will as well lead to an anomaly. And based on this, we can perform an analysis and understand in detail what's going on. And as well, we can check here again the summary to see like the different statistical parameters for each split calculated, so we can understand it as well better. And based on this, we can perform the root cause analysis and identify the areas which are having caused such a certain scenario. But sometimes we are not that lucky that we have a label like telling us our machine is going to fail or not going to fail. So now let's go back to the beginning, and now let's imagine we don't have that label of the machine failure. So now maybe instead, like we say, we don't have this machine failure, maybe we only know all the other columns, and now we want to know, for instance, based on the tool wear, how long the tool was equipped, how many minutes, we want to know if we can identify areas where the machine is going to fail or not going to fail. So now as well, we would need to deselect for sure the machine failure, what we did. Again, we take the statistical recommendations. And now we would be able, again, in this case, let's do it automatically, find the best split of the tool wear. And in this case, this tool wear already can be split into 6 different regions, which would behave differently. Some would relate to a higher tool wear, and some would relate to a lower tool wear. And now, for instance, based on the air temperature, again, we could create another bucket where 818, for instance, in this case, would belong to. So same thing we just did with labels, as well we can do with numerical values, where we can use them to split down the data set into areas which are behaving similar and as well non-similar, which in that mean would behave not like a standard deviation, and based on those buckets, they are more likely that an anomaly will be occurring. So for instance, here we're having an area around a tool wear is between 305, 309, and as well like some higher, and as well same story here. We could now close down that tree again and select for an automatic grown tree to figure out directly what the optimal tree could look like. And we could understand those buckets where would belong together or not would belong together. And those decision trees are typically one of the best tools you can use to perform your root cause analysis. Because in the end, what we want to know is like why a certain part has failed. And based on the decision tree, now we can simply say, if we go back to our example, based on the decision tree, we can simply now say, okay, due to a high torque, and we're quite likely already know that we need to focus more on the area around the high torque because there's something going on. And when we, additionally to the high torque area, check out the tool wear area, when the tool is equipped a long time and the torque is high, then it's quite likely the machine is going to fail. And I should avoid this scenario because then failures are going to happen. I need to spend more time focusing on analyzing these scenarios to understand better why this is happening. That's a perfect tool to do this for understanding where machines are going to fail, where products are going bad. That's why if you have a longer production line and you want to check like why certain tests are going to fail, end of line testings. There are a lot of different use cases where root cause analysis are a super nice feature helping you to understand what's going on or not going on. And with that, I'm at the end of my presentation, and feel free to reach out for any questions. And if there are not any questions in the chat, I will now close this session. Enjoy the rest of the week, and thanks a lot. Bye.